Okay, welcome to week 5 discussions. We have 5 problems. 2 of them will cover Reynolds transfer theorem, and the last 3 are about Bernoulli's. And I'll talk about it then. So let's look at this problem. Here's our schematic. So in our schematic, we see that there's a nozzle shooting a jet of water onto a plate. So we've seen this before. When it hits the plate, the water obviously impinges, and the force from the fluid is transferred to your plate and the cart. In this case, though, this cart is not fixed to the ground. There's rollers, there's wheels on it. So therefore, your plate is going to start building up some kind of velocity, and eventually it's going to reach some kind of constant velocity. And just roll at that constant velocity, which is VC. We're interested in finding what is the reaction force of the plate in order to maintain that constant velocity. So that's our find. And to have the plate roll at constant velocity. So in regards to the fixed plate problem, there is a similarity, ironically, but it's that when the plate is static or not moving, and when the plate is moving at a constant velocity, in both cases, acceleration is 0. So therefore, your force equilibrium should result as 0 as well. So just something to keep in mind for this problem. And in terms of we're given fluid properties like, what speed the fluid's coming in at, what plate your cart's moving, we're given the speeds, we're given density, and we're given the geometry of the problem, the cross-sectional area for the inlet outlets. So we have all these given stuff. We can definitely solve this problem. Before we start, though, let me draw a free bar diagram. Or even before that, I should say that, when the nozzle shoots in the fluid, when the jet hits impinge on the plate, that's the force due to the fluid. As a result, we should expect some kind of reaction force from the plate to hold or to basically counter the fluid force to maintain our constant our force equilibrium and maintain our constant velocity. But there is an additional force factor that I did not really mention, but I feel like it's important that I say it. But pressure force exists. It exists on all of your control surfaces. So obviously, with a pressure difference, it would basically allow your fluid to flow. That pressure gradient drives fluid flow. But even when it drives a fluid flow and causes a fluid force, that pressure term is still there, and that causes additional forces that we should account for. Okay, so let me draw a free body diagram. So here we have our plate on a cart. And we're experiencing fluid force, reaction force, and pressure force on all surfaces. So that's our free body diagram. And quickly learn some assumptions. And we're using standard assumptions we've been using whenever we deal with these momentum problems, which is steady state and 1D inlet outlet. Okay, let me quickly jump back and talk about Reynolds transfer theorem, because that's usually where I like to start. We know that the definition of force is time derivative of mass times velocity, or your momentum. It's the time derivative of your momentum. That's what force is. So either you do time derivative on velocity, which then you get mass times acceleration, or the time derivative is applied to your mass, which then gives you mass flow rate times velocity. So either or, tomato. So we want to put this linear momentum term into our Reynolds transfer theorem. So Reynolds transfer theorem, time derivative of momentum for your system equal to time derivative of integral of your control volume, rho v times your d volume, plus integral of flux on your control surface, rho v r times vr as the vector vr, dot with your normal direction to your control volume, times dA. And this equation, I believe, will be on your final equation sheet, and I think midterm equation sheet too. We assumed steady state earlier, so that means our time, your time term will go away, or your time derivative term will go away. And 1D inlet outlet, our integral simplifies to just a summation. Okay. So here we see that your time derivative, as we've shown in the first line of equations, that's just summation of forces. Quick thing to note, we're interested in finding the reaction force on the plate. Our plate, given this coordinate system, is perpendicular to the x-axis. Therefore, we're only going to care about forces in the x-axis. We're going to neglect all any y forces. And as shown in the second image here, your outlets are y component only. They're only y components. So we only care about the inlet. Just something to note as you go through the problem. So summation of force in the x equal to summation of outlets, because outlets go along with the normal direction. That's why it's positive. Inlets go against it. Rho a v dot v, because v is your intrinsic property, which is like the beta term, minus summation of inlets, rho a v dot v. And I should mention these are v sub r. So before I go on, remember, our inlets are y components. We're gonna ignore them. So this VR term, so we have VJ. VJ is speed for the jet. We have VC. VC is the speed of the cart as it rolls along at a constant velocity. In your equation sheet, you'll see that it says when you work with Reynolds transport theorem, we work with VR. VR refers to what is that? I think it's resultant velocity. I need to double check, but yeah, resultant velocity. And the reason why this velocity this term is important is because we have the speed of the jet, of course. The jet is shooting the water out at 20 meters per second. And when it hits the cart is initially stagnant, then it starts rolling and it's speed until it gets to 15 meters per second. When the cart gets to 15 meters per second, your jet uses 15 meters per second to catch up to the cart. So then only 5 meters per second is left to enter your control volume because, once again, 15 meters per second is used to chase it. Therefore, VR is important because this value is the amount of velocity that's entering your control volume. Therefore, VR is VJ minus VC because 15 meters per second of your 20 is used to catch up to the cart in the first place. That's why only 5 meters per second can enter your control volume. Okay. So let's start with the left side. Summation of forces. And this summation refers to all the red terms I have here. Once again, we only care about the x component. So we have pressure force acting from left to right, minus pressure force acting from right to left, minus Rx, because I'm assuming that reaction force acts to the left. And based on my coordinate system, which is positive y pointing up and positive x pointing right, Rx is going to be negative, is equal to my outlet is going to 0. My inlet has x component. So it's equal to negative rho AV dot V in. And so obviously these two pressure terms are the same, so gauge pressure 0, these terms will go away. I guess one thing to note real quick is that if you were to look at a force summation, like the full force summation, it should look something along the lines of your reaction force plus your fluid force. If we were to move all the terms to one side of the equation, it would all equal 0. And that would make sense because, as I said earlier, when you sum up all the forces, it should equal 0 to have your constant velocity. So this is what this equation is meant to be, but due to Reynolds transport theorem, your fluid force term is automatically moved to the right-hand side. This is how it is. Okay, so reaction force is equal to negative rho. Rho is, I believe, given as 1,000 kilograms per cubic meter. Your area, the jet was given to be 3 centimeters squared for the jet nozzle area. We want to work in meters, so we're going to divide by 100 square to go to meters cubed or squared, times resultant velocity squared, because there's 2 of them. So 5 meters per second squared. Therefore, your reaction force is equal to negative 7.5 newtons. So you see, we account for the fact that the resultant force is going to the left. Therefore, these negative terms cancel out, and we get a positive value. So the reaction force pointing to the left is 7.5 newtons. Any questions on that? Yes.
On the midterm, will we have to specify left or right?
You make your own convention. I mean, I guess it's important to keep track what's positive, what's negative, so it is important. But yeah, you decide. I mean, you could put the reaction force to be pointing right instead of left, like me, and then you'll get a negative answer. So that's it. Okay. Okay, if not, let's go to our last Reynolds transport theorem problem and then move on to Bernoulli's. Okay, so here we have a wind tunnel configuration. We have air coming in on the right-hand side, and your air will then go to this neck region, which is the test section. And in this test section, there are 1,200 holes at the top of your test section, which is sucking out air in order to create some kind of artificial boundary layer. The remaining flow would then flow out through the other side of the wind tunnel via the fan that is sucking the air in the first place. So that's the whole configuration setup. That's your schematic. And we're interested in finding the fluid velocities at certain locations within this wind tunnel, as shown here in A, B, and C above. We're given some values, like while we're trying to find the velocity for certain sections in your wind tunnel, you're given the velocities at other sections of the wind tunnel, as well as you're given the geometry, the cross-sectional area at those locations. So we're given a good amount of terms to solve this problem. We're given, again, geometry, cross-sectional area, and flows at certain areas, such as flow of air getting sucked out of the test section, as well as the flow coming into the test section, for example. Okay, when I see this kind of problem, I always, in terms of control volume, I look for junctions where I see the different flows interact. And for me, I see that this is right here in the test section, because that's where there's an inlet, there's an outlet, or the main inlet, main outlet, as well as where the suction is occurring. So that's a good junction point for me. So this control volume, I can then use Reynolds transport theorem, and considering the fact that I'm interested in finding properties such as velocities, and I'm given cross-section area and those kind of terms, it's most likely that we're going to be using the mass conservation equation in order to get our values, because we just want to solve for velocity. We're not trying to solve for force or anything like that. So the mass conservation equation based on Reynolds transport theorem is 0 first, because the time derivative of mass per system should not be changing, should be 0, is equal to time derivative of your control volume, rho times d volume, plus integral of your flux on your control surface, rho v vector dot normal times dA. That's equal to 0. I forgot my assumptions real quick. And I'm going to make some assumptions, and it's the same assumptions as the last problem. I'm assuming steady state, and I'm assuming 1D inlet outlet. Therefore, my time derivative terms get turned to 0, and my surface flux terms get broken down into summations. So I have 0 equals summation of outlets, once again because outlet goes out, outlets go with the normal direction. Rho AV minus summations of inlets, rho AV. In this control volume, my inlet is the flow at section 1. That's the inlet going into my system. In terms of outlets, I have the suction occurring at the top of the test section with the 1,200 holes. And then I have my section at 2, which is where the flow then exits toward the fan before it exits the wind tunnel. So my outlets were the suction section and section 2. So rho AV suction section plus rho AV section 2 minus inlet rho AV section 1. We weren't given any description of the temperature changing in our wind tunnel, we're also not given that there's any different kind of air, like different kind of gases flowing through a wind tunnel. Therefore, we assume that all these density values are just the same air, and they will all we can divide the entire both sides by rho and get rid of it. So we remove density, so we get 0 equals AVR plus area velocity 2 minus area velocity of 1. And this is just volumetric flow rate. So we reduced our mass flow rate problem to volumetric flow rate, or conservation of mass to conservation of volumetric flow rate. So now we gotta ask ourselves, can we solve for any of these volumetric flow rate terms? And the answer is yes. Look at test section 1, or I guess in the problem statement, we see that test section entrance velocity is V1 equals 35 meters per second. So we have like a velocity value, and for volumetric flow rate, it's area or cross-section area times velocity. With velocity, do we have cross-sectional area? And the answer is yes. Test section is given with diameter of 0.8 meters. That's your cross-sectional area. Q1, A1, V1. A1 cross-section area was 0.8 meters, so you square that because pi over 4 times d squared. And your velocity was 35 meters per second. Therefore, Q1 is 17.6 meters per second. So that's Q1. Our equation still has two unknowns, so we can't really solve it yet. It should be one unknown per equation. So can we solve for something else? And the answer is yes. We're told that, first of all, the test section wall contains 1,200 holes, as we talked about, and each hole is 5 millimeters in terms of diameter. I just realized, per square meter of wall area. So I guess we have multiply that by 4 as well. I'll remember to do that. So 1,200 holes of 5 millimeter diameters per square meter of wall area. Okay, anyways, we'd solve for Q2. Q2 is cross-section area at, QR, cross-sectional area at R times VR. So we have 1,200 holes, as we said earlier, times cross-sectional area, which is the 5 millimeters diameter holes. So pi over 4 times 0.005 meters for 5 millimeters squared, times velocity, which is 8 meters per second. That's the suction speed going out of your hole. Okay, so once again, this 1,200 holes is with respect, it's 1,200 holes per, yes?
The units would be meters cubed per second, right?
Yes, that's correct. It's 1,200 holes per square meter along your test section. So the holes are all around your test sections. Our test section is a cylinder, so we need to get the surface area for a cylinder. So we're looking for SA cylinder. And that would be, so it's a circle, or it would be perimeter of a circle times the length of your cylinder. So 2, or I guess pi d for diameter. So you look for pi times d times L, which is surface area formula for cylinder. So pi times 0.8 meters times 4 meters, and this is given in the geometry of this problem here. And this is pi 0.8 times 4 meters. That is 10.05 square meters. And it's 1,200 holes per square meter. So we got to multiply this value by your surface area of a cylinder. So it got a little messy, but we can still do the math. This term is just based on the amount of holes on your, the amount of holes. I know that this is just the amount of holes that exist. Okay. Therefore, QR is equal to 1.89, or just 1.9 cubic meters per second. That's your volumetric flow rate due to suction out the holes in the test section. Okay, so back to our original equation. We have two knowns. We can now solve this three-variable equation. So I'll rewrite it. So Q2 is equal to Q1 minus QR. Q1 is 17.6 meters per second. QR is 1.9 cubic meters, per second. Therefore, I get Q2 is 15.7 cubic meters per second. So initially Q1 coming in at 17.6, it gets diverted due to the suction of about 2 cubic meters per second, which leaves 15.7, finishing the rest of the way through your wind tunnel outside past the fan. Okay, so we have all of these volumetric flow rate terms. We want to find velocities at these sections at 0, 2, and F. So I made a control volume at the junction, but technically there are control volumes here too. At these two locations, there's also a control volume. But it's kind of arbitrary because it's just one inlet, one outlet. Therefore, it's just the same thing. So mass flow rate at 1 is mass flow rate at 0. And mass flow rate at F, fan, is mass flow rate at 2. Density is the same, so it's just saying QF is Q2, and Q1 is Q naught. That's all it's saying, because inlet, outlet, just one inlet, one outlet. Okay, so Q1 is also Q naught, and Q2 is also QF. First up, I think they said they want to find V naught. So it'd be Q naught equals A naught V naught. We have Q naught. We just got to find A naught. So V naught is Q naught over A naught. Q naught is 17.6 cubic meters per second. A naught is pi over 4 times the diameter. Diameter at the 0 is, I think that says 2.5. 2.5 meters squared. Therefore, velocity at the entrance would be 3.58 meters per second. That's the entrance speed. Next up is velocity at V2, so right after the test section of the wind tunnel. So Q2 is A2 V2. V2 is then Q2 over A2. So that's 15.7 cubic meters per second divided by pi over 4 times the diameter. Test section diameter is 0.8 meters, so we'll put that in there. 0.8 meters squared. That's equal to 31.2 meters per second. Finally, at the fan, volumetric flow rate at the fan is area at the fan, cross-sectional area at the fan, times velocity at the fan. And then velocity at the fan is equal to QF over AF, which is 15.7 cubic meters per second divided by pi over 4 times diameter at the fan location. Diameter here is 2.2 meters. So 2.2 meters squared. That's equal to 4.13 meters per second. So we solve for the velocity at each of these locations that we care about using Reynolds transfer theorem and conservation of mass. Any questions on that? Okay, if not, let's start with Bernoulli's. So here I drew a diagram for us. Let's talk about it. So on the left-hand side, this once again Bernoulli's equation. Bernoulli's equation is a summation of 3 energy terms. It's your internal energy, it's your kinetic energy, and it's your potential energy. A similar version of this equation exists for mechanics, like physics mechanics, but for fluids we have our own version. It works in terms of pressure, and I guess pressure is it's a form of pressure energy. So here in this diagram, I have fluid going up this pipe, and let's see. So let's talk about my energy grade line. As I mentioned, when you sum up all three terms, you get the total energy for that fluid. That's your energy grade line. So within that tube, no matter where you are in the tube, if you sum up all your energies, you will end up at the energy grade line. Now there's a hydraulic grade line, which is if we neglect any kinetic energy terms. You see there's two pipes. One of the pipe is kind of chilling at the edge of the pipe or the tube. The pipe chilling at the edge of the tube cannot record any kinetic energy. It can only record internal energy and potential energy. That's a hydraulic grade line. It cannot record the velocity. But the tube that's stationed right in front of the moving velocity or the moving fluid, you can then record the kinetic energy for that section. And that's the tube that gets you to the energy grade line. Otherwise, when you don't put your tube there, you only get the hydraulic grade line. Okay. So that's Bernoulli's equation. It's just the combination of those three energy terms. Something to note is when you use Bernoulli's, you gotta assume these 5 things. You gotta assume that you're in steady state. Steady state. You gotta assume that it's a frictionless flow and viscid. There's no viscosity terms, no shear stress. You gotta assume that it's an incompressible flow, meaning the Mach number is below 0.3. You gotta assume that you're part of a streamline. So you see in this tube, we're in a streamline. If you're in another tube that's a different streamline, you can't really use that same. You can't compare different tubes, essentially. And 5, there's no change in energy. Because if there's work being done or heat transfer occurring, your energy grade line will be moving in that case with that 5th condition. So therefore, if your energy grade line is moving, what's the point of having the two things be equal to each other? Unless you account for that. So those 5 assumptions are going to be made every time we do Bernoulli's equation. These 5 assumptions will be made. So for example, that wind tunnel where there's a fan, if we were to pick a point past the fan, you can't use Bernoulli's because there's work being done by the fan. Okay. Any questions on Bernoulli's? If not, let's do a first problem. So here we have kind of like a sippy cup and a straw coming out of it. And here's that's a schematic. We're interested in finding the velocity exiting our straw, which is V2. Find V2. And at least initially in part A, we're not really given much variables. That comes in part B. But we can assume that we're given most of the important variables that are needed in order to solve for the basic Bernoulli's equation, which is, internal energy, kinetic energy, and gravitation, potential energy. Okay, so in terms of the Bernoulli's equation, if possible for me, you want to try to cancel out the internal energy term if possible, because that's probably the most annoying thing to deal with. For example, if I pick the point inside this fluid, right, essentially, I have to account for the height of the fluid column above it, and that's, specific weight times fluid column height. It's kind of annoying to deal with. I'd rather have it so that internal energy cancels out, if possible. So in this problem, I see at location 1, we're sitting, that's like the surface of the water is sitting right in front of the atmosphere. Therefore, it's experiencing atmospheric pressure at that location, just atmospheric pressure. No fluid column height or anything, just that. And same for the exit of the straw, because when the fluid exits the straw, you're back at atmospheric pressure. So if possible, I want to work with locations 1 and 2. And just to note, we're setting location at the bottom of this cup as 0. That's just our arbitrary datum. That's what it's called. Okay, so once again, I want to use point 1 and 2 if possible. Let me do that. So Bernoulli's equation, and I guess we're given this in part B, but we're going to assume those 5 things above. Okay, so therefore, if we assume that, internal energy plus kinetic energy plus potential energy of location 1 is equal to internal energy plus kinetic energy plus potential energy of location 2. Once again, those internal energy are just atmospheric pressure, so they'll just cancel. One thing I forgot to talk about real quick is within this cup, before you enter the straw, which obviously the fluid's moving and is moving in a streamline, right? While you're in the cup still, that's hydrostatics. And you can imagine hydrostatics as everything that's not moving is part of the same streamline, essentially. That's why we can use Bernoulli's, because it's all part of the same streamline in hydrostatics. But yeah, hydrostatics, location 1, hydrostatic means V0, so we can cancel this term too. there's only 3 terms left we got to deal with. We want to solve for V2 or find an expression for V2. So then I do, so rho GH1, I bring this rho GH on the right-hand side to the left-hand side, minus rho GH2 equals 1/2 rho V2 squared. Therefore, rho 2 is equal to square root of 2 times rho over rho G H1 minus H2. That's our expression for V2. Now I want to plug in values to solve for volumetric flow rate that's exiting the straw. So V2 is equal to 2 times gravity. On Earth, that's 9.8 meters per second squared. And we want the difference in height. We're given that at location 1, we're at 60 centimeters, 0.6 meters. And at location 2, we're told that we are at negative 25 centimeters. But considering that our datum is here, it just means that we're 25 centimeters below our datum, or our datum. So minus negative 0.25 meters. And all of that is square rooted. Therefore, V2 is equal to 4.08 meters per second. So that's this exiting speed, but we want volumetric flow rate. So there's an extra term, which is the cross-sectional area at the exit of the straw. We're given that the tube diameter is 1 centimeter, so we solve our A2. So 4.08 meters squared times pi over 4 times the diameter squared, so 0.01 meters squared. That gives me 3.21 times 10 to the power of negative 4 cubic meters per second. We want this thing in centimeters, so we got to divide by 100 centimeters cubed for a cubic meter. And this just gives you 10 to the power of negative 6 because it's just 100 to the power of 3, so 10 to the power of negative 6. Therefore, we're left with 321 cubic centimeters per second. That's your volumetric flow rate, That's your volumetric flow rate. Any questions? Yes?
How'd you get 0.01?
So area is pi over 4 diameter squared, right? So diameter is given here where it says the tube is 1 centimeter in diameter. Okay. Any other questions? All right, let's keep moving. So next up, we have a fire hose. So, the firefighter will attach the hose to a hydrant, and the hydrant will pump water through your hose. And water goes through the hose, and then it gets to your nozzle, where the flow gets accelerated due to change in cross-sectional area. And that shoots out the water at very high speeds. In order to even do that, a pressure difference must be present, because obviously pressure difference drives flow. Flow goes from high pressure to low pressure. That's how it works, because the higher pressure would obviously force the water towards the direction of the low pressure. So here's our schematic. That's our hose with the cross section suddenly changing to be very small, and the flow then accelerates. We're given cross section area. We're also given very important term. We're given volumetric flow rate going through this our system, and we want to find the pressure difference. Where to say that? Find what pressure must be maintained. I'm sorry, it wants pressure maintained. So I guess it wants pressure at 1. Okay. And we're assuming that when the water exits, we're at atmospheric pressure. Because, once you exit the hose, you're back in the atmosphere. So I'm going to make my assumption, obviously assume 5 conditions. And therefore, I get internal energy plus kinetic energy plus potential energy at location 1 is equal to internal plus kinetic plus potential at 2. So we're going to assume that based on this schematic, our hose, we're at similar heights. So even if I set my datum here, at locations 1 and 2, it'll be the same height from that datum. Therefore, these terms cancel out. Okay. We're interested in the pressure upstream of the nozzle. that's P1. That's at location 1. That's where the higher pressure is to drive the flow to the lower pressure at the nozzle. P1 equal to P2, which is atmospheric pressure, PA, plus 1/2 rho V2 squared minus 1/2 rho V1 squared, because I move this term from left hand to the right hand side. So therefore, P1 is, we're working in English units, so 14.7 pounds per inch squared times 144 inch squared per feet squared, because we want to work with feet, plus 1/2 times rho, density of the fluid, 1.94 slugs per cubic feet, times my velocity, the difference of my velocity squared. So I need to get those terms actually. We're given volumetric flow rate. So volumetric flow rate is the same because we have one inlet, one outlet, so both Q's are equal to each other. It's 250 gallons per minute traveling through your nozzle. No, it's 250 gallons traveling through your nozzle. We want to convert. So to convert gallons to inches, we do 231 cubic inches per gallon. We want to go from inches to feet, so it's 12 to the power of 3 cubic inch to cubic feet. Then we want to convert from minutes to seconds, so it's 60 seconds per minute. And everything will cancel out to give us cubic feet per second. Therefore, volumetric flow rate is .557 cubic feet per second. That's your volumetric flow rate, and it's the same at point 1 and point 2. Volumetric flow rate is area times velocity. We know the cross-section area, so we can get velocity. Q over A, 0.55 cubic feet per second, divided by pi over 4 times the diameter. For location 1, diameter is 3 inches. 3 over 12 to get the feet squared. Here I get 11.35 feet per second for velocity at location 1. At location 2, same concept, Q equals A2 V2. V2 is Q over A1, which is 0.557 cubic feet per second, divided by pi over 4 times diameter squared, 1.125 divided by 12 feet squared. That gets me 80.69 feet per second. So as you see, we diameter, basically we half the diameter, and basically the flow speed kicks up by nearly a factor of 8. Okay, we have our velocities. We can now go back to our Bernoulli's equation and solve for P1. So here it's velocity 2 first, so that's 80.69 feet per second squared minus 11.3 feet per second squared. Therefore, the pressure upstream needed to maintain that this flow and the acceleration of the fluid should be so atmospheric pressure is 2,117 pound force per feet squared, and the pressure difference due to accelerating the flow would be 6,190 pound force per feet squared. So assuming atmospheric pressure at location 2, the total pressure needed at location 1 to maintain that pressure, or to maintain that fluid flow would be 8,307 pound force per feet squared. So this is the case of using Bernoulli's equation to solve for pressure. Usually we want to cancel out pressure, but sometimes we got to solve for pressure. Any questions? Okay. If not, let's jump to the last problem and we're done. So this last problem here, we have an aircraft flying at 300 miles per hour. So I'm going to label this VC for the aircraft, 300 miles per hour. And we're flying at an altitude of 4,000 meters. So we're told that the air velocity on the upper surface of the wing at the maximum thickness is 26% higher than the speed of the aircraft. So what they're saying is velocity at upper surface divided by velocity of the aircraft is 126%, which is 1.26. We're interested in finding what is the absolute pressure at the upper part of the wing given this velocity, or I guess velocity ratio / difference. So, yeah, let me draw a schematic. Here I have my wing. So, maximum thickness usually occurs at the quarter chord length, so like a quarter of the chord way down. And there we have our upper velocity at the upper surface. And at the velocity at the upper surface, we also have our upper pressure term there too. So our aircraft, or I guess our wing, our aircraft is flying into the wind at 300 miles per hour. But the logic is that this is the same effect. You flying into the wind at 300 miles per hour is the same effect as the wind blowing into you at 300 miles per hour. That's how wind tunnels work. They use that the opposite effect. So therefore, we can represent the flight of the aircraft as incoming wind. So we have VC coming in, which is associated with PC. And we're going to use Bernoulli's, which is fair. But in Bernoulli's, what we're assuming is we're part of the same streamline. Therefore, what we're assuming essentially is that the flow first, I guess, comes in contact with your wing, and then no slope condition kicks in, so that your flow can basically grab onto the upper surface and follow along it in a streamline. Which is it's an okay assumption, I guess. But there, so now we have a streamline, so we can do Bernoulli's. So those are all our terms because we can neglect elevation changes. So that's something to note. So if I set Bernoulli's equation with this setup, internal plus kinetic plus potential for the incoming wind equal to internal plus kinetic plus potential of the upper surface. We neglect elevation changes. So we're left with PC plus 1/2 rho VC squared is equal to P upper plus 1/2 rho V upper squared. P upper is then equal to PC plus 1/2 rho VC squared minus 1/2 rho V upper squared. So we have our equation. We've got to find these values and substitute them in. So let's first start with VC. So we're at 300 miles per hour. We want to convert to SI units. So first, I take out the mile. 1 mile is 1,600 meters. And 1 hour is 3,600 seconds. Therefore, my speed is actually 133.3 meters per second. Let's move to this next given variable. We're given altitude. In the recording, I'll show it to you guys, but essentially there is a table that correlates your altitude in the atmosphere to pressure, density, temperature, viscosity, those values that are important to fluid mechanics. Based on the equation that we saw from Bernoulli's, we just care about pressure and density. So at 4,000 meters, we're looking at a pressure of 61,633 pascals and a density of 0.8191 kilograms per cubic meter. So as you see, at 4,000 altitude, meters of altitude, your pressure basically halves from standard atmospheric pressure, and your density is about 30 to 40% less than what it should be at sea level. And here, V upper is 26% greater than VC. So let's rearrange our equation and get an answer for V upper. So 1.6 times 133.3 meters per second. I get 168 meters per second for V upper. So I have all my terms I need. I can now solve. P upper is 61,633 pascals plus 1/2 times density. Density is 0. Oh, yeah, gotcha. Yeah, I can't see either, but yeah, here we go. 0.8191 kilograms per cubic meter times the velocity, the difference of velocity squared. So VC, we discussed, was 133.3 meters per second, so we square that, minus velocity at the upper surface, which is the higher one, 168 meters per second squared. Therefore, we get the P upper is 57,351 kilopascals. So that's the absolute pressure on the upper surface of your wing. So I think it's like the very well, I mean, I guess it's an explanation, kind of. But assuming that, so 57 kilopascals, assuming that your bottom surface of the wing has the same velocity as your incoming velocity, it has a similar pressure value. So therefore, the pressure down at the bottom, roughly, would be like 61 kilopascals. And therefore, as you see, we have a pressure difference between your upper and bottom surface. And as a result, there's some kind of lift force that occurs. And that's like one of the ways to explain lift, I guess, with Bernoulli's, but
Wait,
not
so
sure.
the final answer is 57.351 kilopascals, right?
Yes, that's correct. Any questions? Yes.
Sorry, I walked out right when you were covering the pressure at sea and the density, but where did you find those values?
Yes, so usually there's a table in the appendix. In the recording, I'll post the table, like somewhere here. But there's a table that associates your altitude with fluid properties we care about, such as pressure, temperature, density, viscosity, etc.
Okay, so on like the midterm or something like that, would we just be given those values straight up, or would we have to look for them through the table?
I don't know.
Okay.
Probably table, that's my guess.
Okay. Then how would we find that if we're not given, I mean, you're kind of relating it to like thermo where we need like pressure and temperature, how would we find those values? Just by looking at the altitude?
Just altitude gives you all those properties.
Okay, sweet.
Yeah, I'll post the table in the recording and you'll see. Any other questions? All right, not, thank you. That's all. And if you want to get your quizzes, it's up here.